All right, welcome on in, everybody. So looks like we are starting chapter 5 here, probability. So probability is kind of a weird chapter in statistics because it's just different than the rest of them, right? You've been learning these statistical tools, and you've been doing the homework and the lessons, and you've been working on your project and using the statistics that you learned in the lessons and applying it to your project and sort of getting all that work together. And then probability is a little bit of a sidestep here, where there's not a whole lot of actual statistics taking place in this chapter. It's largely about probability, and then there are some hints and some information in this chapter about how to apply that probability to statistics. Okay, so it may seem like we don't do a whole lot of statistics in this chapter. That's because we don't. But you could argue that, the argument could easily be made that if you don't understand probability, you can't do statistics, right? And I would say that's true. I think that's a true statement. And probability is really important for you to understand anyways, right? It's one of those skills like, the question, the proverbial question of when am I ever going to use this? Yeah, there's a lot of stuff that you've been taught in your math classes that you're probably never going to use again. The vast majority of you will never factor a difference of cubes ever again. You did it on your way to get here in an algebra class, but probably most of your futures do not involve factoring difference of cubes, right? It's not one of those skills that's really important unless you're someone who's going to use difference of cubes. Then it's important, but most people don't. Probability is not one of those, right? See, the way math works is kind of weird sometimes. Like you never hear people go, "Oh, when am I ever going to use reading? Why do I need to learn to read?" Even though most people don't read, right? Most people don't read very much. Even if you give people stuff that's even 3-4 sentences long, they just kind of skip it and then ask you what it says. But reading's one of those skills that everyone kind of understands is important. A lot of math is that way. There are certain mathematical topics that you can use in your everyday life to make better decisions. Probability is one of those, right? If you understand probability, you will be able to think a little bit further in problems in your everyday life and make better decisions. People try to do this now. People sort of, even if people have never been exposed to probability, they sort of try to use it, right? You've been probably been hanging out with people before when someone says, "Well, what's the probability of that happening?" Well, if they don't understand how to calculate probability, they don't have any idea what the probability of that happening is. Sometimes it's more often than you would think because there are factors involved that are not necessarily obvious that make the probability greater than you would expect it to be. Sometimes it's the other way around, where the probability is lower than you would expect it to be, right? This is part of what they do in casinos. They make you think that, you have some kind of advantage when really the house has the advantage, right? And most of those games, craps and, any of them, you sit down and calculate the probabilities, you can see you have a definite disadvantage sitting at that table, like a mathematically calculatable disadvantage sitting at the roulette table. You play long enough with the roulette table, you're going to lose all your money. But that's not the only place you can use these. You can use these in all sorts of decision-making process. Anything where something has a probability of occurring, you can use this kind of information to make assessments, right? Should I get this type of insurance, or is it okay not to have it? Should I get earthquake insurance? Should I get, all these other things? People are just kind of guessing in the dark unless you know basic probability. So that's what we're going to be looking at. And again, this is one of those chapters you should be able to carry over and use in life. Now, not every single thing in the chapter you'll use in your everyday life, but a basic understanding of probability really can be helpful. So we're going to take a look at that, and we're going to try to bring up some topics that are going to make sense, the future tools that we're going to be using in this class. So a lot of things we're going to be using going forward involve a p-value. That p-value stands for probability. That is, what is the event that this probability would occur under these conditions? Now, the good news is most of the time StatCrunch is going to calculate that p-value for you. But it's like anything we do in mathematics. If you just sit there and you wait for the computer to give you a p-value, but you don't really understand what the computer's doing, you don't really understand how probabilities work, then you don't know what you're doing. You're just sort of still just sort of randomly making guesses in the dark. So that's why it's really important that we understand probability, not only to understand the rest of the material we're going to go through. Hypothesis testing, confidence intervals are two of the big ones that really only make sense with an understanding of probability. And there's a few chapters at the end look at confidence intervals, hypothesis testing, little bit of stuff along the way. We need probability to understand what's going on there. Okay, so that's where we're going to kind of shift our attention here. Okay, so for starters, here's a situation. So this is a book. Remember, this is not the textbook we're using, but it's similar. It's the same ideas of the same stuff. Like it's a different book. I just looked up Triola PDF or something like that, and I was able to find a PDF of an old. It's like an out-of-date version of the book. It's not the current version, but that's okay because the statistics hasn't changed much in the last few years, like the basic statistics. So, here's an example they give in the book: pre-employment drug screening results. Right? You may have this. You may work at a place where you have to be drug screened. Right? I think certain types of things that have to do with corrections or law enforcement, they sometimes have drug testing. Certain businesses, I have friends who work at companies that are, just like electric companies and stuff like that. They have to be drug tested and stuff like that. So different scenarios, and you might think, well, it's pretty simple. You go get drug tested, and it either says positive or it says negative. So either they found drugs in your blood or they did not, right? It's a little more complicated than that, and that's why we have to be able to think deeper about probabilities in order to really understand and make an assessment of the probabilities involved. Okay? We have to understand what the possible outcomes are, and we have to understand how many different ways those outcomes can occur. Right, because we have there's actually a few different types of probabilities. So we first have to identify what type of probability we're dealing with, and then we have to investigate, under what circumstances can these things occur? Then we can start to unravel probabilities. And probabilities are tricky because, the very, very basics of probability are just sort of super simple, right? Like when we look at the basic definition of probability, you go, okay, that's pretty easy. But it can get complicated pretty quick. And it can get to the point where you might read a problem that sounds really simple, but calculating the probability is actually a lot more complicated than you would think. That's why, like I was talking about earlier, where sometimes you're having a conversation with someone, they're like, well, what's the probability of that happening? And then you go, actually, it's more than you'd think, right? So something that might seem like a long shot, when you investigate what's actually happening, not so much of a long shot. So here's an example they give just to kind of help us understand there's more than one, like you go in for a drug screening test. You either test positive or you test negative, but it's more complicated than that. There's actually 4 outcomes. If you think about it, there's 4 different possibilities for someone going and getting drug tested. So the people that go in before they take their drug test, they're already in 2 different categories. Okay, you have the people who have used drugs, whatever, and by drugs, just sort of a general term. Right? It sounds silly, like sort of grouping everything as drugs. But in this case, the assumption is that we're talking about some type of illicit drug that is illegal. So whether it's, marijuana or heroin or, meth or whatever it is, it's whatever this place was screening for. Okay. Well, when people first go in, you already have people in 2 groups. You have the ones that use drugs and the ones that do not use drugs, right? So at first you just think of it's just everyone's the same going in and getting the test. No, there's already 2 different categories. There's the people who have used drugs and the people who haven't. And then for each of those 2 groups, there are 2 outcomes, okay? Either the test comes in positive or the test comes in negative. And, drug tests are one of those things that are not 100%, right? You're going to get a small percentage of errors depending on which test you're using. That can be a larger portion of errors to a a smaller portion of errors. But even if something is, 95% effective, like a lot of times people hear that. Like this is one of the reasons to understand probability, right? We saw this in the news in the recent past. Something's 95% effective. People just sort of assume that means it's like 100% effective. Like that's what people hear. Oh, 95% effective? Okay, I can totally trust this thing. It's basically 100% effective. But you need to understand the probabilities involved, right? So the thing that's been in the news the last couple of years, so the vaccines, kind of both of them are right around 95% effective. And people just went, oh, okay, well that means that then you're fully protected if you get it. No, 95% effective means that it's not gonna work 5% of the time. It's 5% defective. So everyone kind of freaked out when there was these breakthrough cases of people who were vaccinated but still got COVID, and they're like, oh, well, see, even people who get the vaccine can still get COVID, right? Because the vaccine is 95% effective, right? Which means 5% of the people who get it are still at risk, right? So you can't just look at it and go, well, we'll see, this person took the vaccine and they still got the virus, so what's the point? It's all useless. Well, if there was some danger coming, and you could be in one of two groups, a group that is 0% protected or a group that is 95% protected, think about it from a probability standpoint. Which would you rather do? You can't, like, one of the things we need to get away from in statistics and probability is thinking about what they call anecdotal cases, right? Where you find one case that goes against what you're trying to look at. And this is the same thing here. Like, well, I'm not going to get the vaccine because my aunt got it and then she still got COVID. So that means the vaccine doesn't really do anything. That's not what it means at all. The vaccine is 95% effective. So if millions of people are getting the vaccine, that still leaves thousands and thousands of people that are still exposed, right? But again, you can either be 95% affected or 0. And I'm not trying to make this class political or anything, but what I'm saying is that's a perfect example of the type of thing that you want to be able to look at with probability, right? Don't just listen to people on the radio telling you this or that. Like, just think about it for yourself from a probabilistic standpoint, and then you can make good decisions about whether, what your course of action should be, not just being swayed by anecdotal evidence, which is not a scientific way of looking at things, right? So the 4 outcomes, right? Someone who uses drugs, someone who does not use drugs, they go in and get tested. Well, the people who use drugs have 2 outcomes. The people who use drugs will either test positive for using drugs, or they will test negative, meaning that they didn't use drugs. Okay. The people who are not drug users will come in, and some of them will get a positive result. Even if you haven't used drugs, you can get positive results, right? There's that error. There's 2 ways in which errors can occur when you go to take a drug test. One is that you do use drugs, but it says you didn't, right? That's the one people are kind of hoping for. They're like, oh, I kind of went to a party last week. I hope this doesn't show up on my drug test. And then they get through, right? And then you have the other one where someone's not a drug user, but the test says that they are. The test comes back positive, right? And then you have, the 2 true cases are someone is a drug user and they test positive for drugs. Someone is not a drug user and they test negative for drugs, right? A lot of times, if you test positive, sometimes places will give you a second test because it's really unlikely that you're going to get a false positive 2 tests in a row. But anyways, without getting into all that, it's just you want to understand, you have to understand all the outcomes if you're going to understand probability. If you can't keep track of the outcomes, you can't even calculate anything in these probabilities, okay? So, and here's what we call the rare event rule for inferential statistics, and this is part of the statistics we'll be thinking about going forward, right? If under a given assumption, the probability that a particular observed event is extremely small, we conclude that the assumption is probably not correct. Now, that's a very scientific way of forming a statement that is going to be the foundation, the theoretical foundation of a lot of our tools going forward. That is, you're going to use StatCrunch to calculate a p-value. The p-value is what is the probability of this thing occurring under these conditions. If that probability is really, really small, then we don't believe it, right? We reject that information. If the probability is reasonable, then we say, yeah, maybe this works, right? This happens all the time when you judge people if they're lying to you or not, right? Someone comes to you and they tell you some story that something occurred, and if they tell you a story that seems pretty reasonable, then you go, okay, I guess that's fine. And you sort of believe what they say, or at least it's not worth like calling them out and telling, calling them that they're lying or whatever. You go, okay, it's possible that what you're saying is true. But if someone comes to you with a story that is so ridiculous that you're like, that never could have happened, then you don't believe it, right? I mean, what if I was late to class and I'm like, well, I was out walking my dog and then I got robbed by a group of clowns and then they kidnapped me and took me to a field and then I was abducted by aliens and then I finally got to class, but that's why I'm 15 minutes late. You'd be like, what? That didn't happen, right? So what you're doing in your brain is you're calculating the probability of his story being true is so small. Like, it's not impossible, but that probability is so small that I don't believe you. Okay, that's what we're going to be doing in statistics. We're going to be using scientific methods to get a probability calculated. And if that probability is so small, we're going to say, yeah, I don't think I believe our situation here. Something must be wrong. And then we're going to reject our assumptions. Okay, that's really important. So make sure you kind of understand that idea. If you don't understand that, then hypothesis testing and confidence intervals really won't make sense to you. It'll just be kind of a thing you're memorizing coming out of the computer, and you can't do statistics that way. It won't make any sense. Okay. Right. So keep that in mind. Okay, some definitions that we need for probability. So an event is any collection of results or outcomes of a procedure. Okay, so again, a lot of this sounds really generic, and you're like, what does that mean? An event is any collection of results or outcomes of a procedure. It's a thing that you're keeping track of when you're calculating probabilities. So for instance, rolling a dice, right? A lot of early probability games are based on dice, coins, and cards, right? So if you could roll a dice and go, oh, there's a 3. Okay, you just kept track of that. That's one event, right? You roll the dice again, it's another event, right? Or if you might be talking about rolling 2 dice. So you roll 2 dice, there was an event, okay? They can get more complicated. It could be pulling a card out of a deck, right? Here, I've got a deck of cards. Pull one out. There, you pull it out. That's your event. You flip a coin. It comes up heads or tails. There's an event. Okay, so really, it just means like the smallest piece that we're keeping track of when we perform an experiment again and again. So we might flip a coin 100 times, right? And we're keeping track of those coin flips. So that's our events. A simple event is an outcome or event that cannot be broken down further into simpler components. So it's sort of the smallest piece you can come up with. You can't make it any smaller. Now, here's really important, this idea, the sample space. This one always kind of takes people by surprise. Everything in probability is built on a sample space. If you don't get sample space, you're basically at step 0 with probability. And that's okay if you're there now, but you're going to have to get comfortable with it because everything you're going to do involves sample space. The sample space for a procedure consists of all possible simple events. That is, the sample space consists of all outcomes that cannot be broken down any further. Okay, so it's just your possible outcomes, right? So if I have a coin and I'm going to flip a coin, what are my possible outcomes? Well, the coin could come up heads or the coin could come up tails. Those are my 2 outcomes. So those 2 things together make up my sample space. And a lot of times what you're really going to be concerned about is the size of your sample space. We're going to learn new ways of counting so that we can count sample spaces that are a little bit more complicated. Okay, because You might go, well, but I know how to count. I've been counting since like kindergarten. Or even before that? What do you mean I'm going to learn how to count? Well, you know how to count things that are in a continuous sequence, 1, 2, 3, 4, 5, 6, and that are relatively small, right? If I asked you to go count the grains of sand down at the pier, right, then like, yes, you can count consecutively, but good luck, right? Those numbers are too big. So that is one problem we have, is that oftentimes in probability, the numbers that you have to calculate are too big to count by hand. 1, 2, 3, 4, 5, 6, 7, right? Just think grains of sand on the beach, too big to count one by one. The other problem is that we're going to get into things that are very, very difficult to count sequentially, right? So if I asked you to count everyone in the class, like if we were in the classroom and I said, count how many people in the class, you'd all just kind of turn around and go 1, 2, 3, 4, 5, 6. Like that's easy, right? But what if I said, okay, calculate how many subcommittees of size 3 can be formed in this group, right? So that is, we want to form a subcommittee. We want 3 people on it. How many different ways can we form a committee with the people in the room? That's all of a sudden a little bit more complicated. That's harder to do because it's not just a matter of counting sequentially. You have to think about all these different combinations and how do you count those combinations in a reasonable way. That's a harder sample space to calculate. We'll learn ways of calculating it, but that's why the sample space, again, it's a simple idea, but some of the problems will get more complex as we do it. So like I said, flipping a coin, your sample space is heads or tails. What about rolling a regular dice, 6-sided dice? What are your possible outcomes? Well, you could roll a 1, 2, 3, 4, 5, or 6. Those are your outcomes, so that's your sample space. Your sample space has size 6, and those are your outcomes, 1, 2, 3, 4, 5, 6, right? What about a deck of cards? What's the size of your sample space for a typical deck of playing cards? 52, right? There are 52 playing cards in a standard deck that we usually play with. You've got 4 suits, 13 cards in each suit, 13 ranks in each suit. That's 52 cards. That's your sample space, right? If someone gives you a deck of cards and says pull out a card, your card will come from one of those 52 outcomes. Okay. And here they just give an example. What about a single birth? Well, you got a boy or a girl. What about 3 births? Now, so here's where it gets a little bit more complicated. What if we say, what is the sample space of having 3 children, right? If you just say, oh, I'm going to have 1 kid, that's easy, boy, girl. We're going to have 3 births. Well, you have a bunch of possibilities. You could have boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. 1, 2, 3, 4, 5, 6, 7, 8. That makes sense that it's 8 because think about it this way. For each child, there's 2 outcomes, right? 2 possible outcomes. So there's 2 possible outcomes for the first child, 2 possible outcomes for the second, 2 possible outcomes for the third. 2 times 2 times 2 is 8 outcomes, and we found them all right here. So see how it's really helpful to be able to calculate both the outcomes in your sample space, but also the size of that sample space. Because if you make your list of outcomes, like here, and you get 7, but then you go, well, wait a minute, I think there should be 8 because 2 times 2 times 2 is 8, then you know you're missing one, and you can find the one that you're missing. If you move ahead and use a sample space with only 7 in it because you missed one, everything's going to be wrong, right? So when you're listing these, try to do it in a systematic way. So this is kind of how it's usually done. See how you start with one like extreme, boy, 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 and then you work to the other extreme, girl, girl, girl. So like the way you would do this is you'd go boy, 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 and then you start with the last one and you change it to the other possibility, boy, boy, girl. Okay, so now we've taken care of all the possibilities that would go boy, boy, blank, right? So then you move the middle one. Okay, boy, girl, boy. Boy, girl, girl. Okay, now we've taken care of all the possible ones that go boy, blank, blank. So now we have to look at all possibilities to start with a girl being born first. Okay, girl, boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. So when you're listing these sample spaces, try to do it in a systematic way. If you're just randomly grabbing an outcome, it's very, very likely that one of two things is going to occur. One, you're going to accidentally repeat one, because if you have a list of 12 things that are like B's and G's, it's hard to sometimes see that the third one also matches the 10th one on your list, and you've accidentally duplicated an outcome. Okay. The other thing is it's easy to miss one. Like I talked about a minute ago, if you just randomly try to put this together, it would be very easy to come up with 7 outcomes and go, I feel like I got them all. I think I got them all. But you wouldn't. You'd be missing one because there's 8 outcomes because you didn't do it in a systematic way. So whenever you're listing these small sample spaces, don't just randomly try to fill in your list. Try to do it in a systematic manner. Trust me, I watch people do it in class. The people that do it systematically, they're done in like no time at all. The people that are just randomly filling things in, they like never finish the problem because you're not going to be able to get there by just randomly looking. Okay. We have some notations that are pretty standard for probability that we need to remember. So capital P stands for probability when you're talking about probabilities. Capital A, B, and C generally denote events. So see this notation here where we have P of A. This is kind of like our function notation from algebra, right? Where we'd have a letter and then some parentheses and then a letter in there. You could think of the probability as being a function. It really means take the probability of event A. So I could say like, what's the probability of rolling a 2 on the dice? That would be P, and then parentheses, you'd have a 2. Now, this has to be in context, right? You have to have already decided what these events are, or people aren't going to know, like, well, what is A? Well, A could be rolling a 2. B could be rolling an odd, or whatever. You have to make that obvious in the problem. So if you're like, well, what's A? Where did A come from? A is just a general term right now, like a variable that stands for a specific outcome. Okay? So we have a few different types of probability, and they can confuse people at first. So we want to be careful with that. So relative frequency approximation of probabilities. Super fancy name. Sounds complicated. And then we have the classical approach to probability, which requires equally likely outcomes. And this is the one that it's a really, really important thing to consider, because if you don't consider whether your outcomes are equally likely, probability gets way, way more complicated, right? It takes a lot more work to figure out the probability problem. So sometimes what people do is they try to apply this method to every possibility of probability, but sometimes it's not the appropriate tool to use, and it will lead you astray, right? So you have to be careful. So what does this mean? This classical approach says you take the number of ways A can occur over the number of different simple events, and then it's just S over N. So let's do an example here. Oops, I didn't clear this out. So let's say we are going to roll a standard dice, right? So a standard dice, your outcomes are 1, 2, 3, 4, 5, 6, right? Just the typical dice. We're not doing like a, 30-sided Dungeons and Dragons dice or anything like that. Just a typical dice that people are familiar with. You've probably rolled a dice playing a board game in your life. Here we go. Roll a standard dice. So let's take a look. So what is our sample space? Our sample space is 1, 2, 3, 4, 5, 6. Right? Just the numbers. Oops. Put my dollar sign in the wrong spot. Actually, I didn't. It auto-filled it in the wrong spot. There we go. Okay, so we know what our sample space is. So we know all the outcomes from rolling a single dice. Okay, so let's say I want to calculate the probability of rolling a 2. Okay, what's the probability of rolling a 2 when I roll a dice? Well, our formula that we just looked at said it's the number of ways that the event we care about can occur. So how many ways are there to roll a 2 when you roll a dice? 1. It comes up a 2, right? That's the only way for it to happen. So our numerator is a 1, And the denominator is the total possible outcomes. Well, how many outcomes do we have? That's the size of our sample space. There are 6 things in our sample space. So the probability of rolling a 2 when you roll the dice is 1/6. Okay. Now that we're looking at it, we should be careful because we want to ask ourselves, what exactly is a probability? A probability is a number between 0 and 1 that represents the likelihood of your event occurring. So sometimes people will give probabilities in a form that are technically wrong, right? You'll hear people, well, what's the probability of this happening? And then they'll talk to you about odds. Well, odds are not probability. That's a different way of expressing probability-related things, but that is not a probability, right? In fact, we won't use that a ton in this class in statistics. I don't remember if it comes up a little bit in the videos, but we won't use odds very much. Okay, we want like real probabilities. So if you ever calculate a probability that is not a number between 0 and 1, then you have made a mistake, right? If you have a homework problem that says what's the probability of this occurring, and you go 3, no, that doesn't make sense. Probability cannot be 3. Okay. So let's calculate some other probabilities that sort of will help us understand a little bit. Okay, what's the probability that I roll an even number? Some of you might even sort of intuitively know this, but you don't necessarily know why. Being able to understand the why will allow you to do other more complicated problems. So what's the probability that I get an even? Well, so we want to count the outcomes that match the event we're looking for. So how many different ways can I roll an even? 2, 4, 6. There are 3 different ways that I can roll the dice and get an even. Okay, 3. And there are 6 total outcomes. So that means that my probability is 1/2. Okay. What if we want, so one you might not be able to do instantly, what is the probability of rolling a prime number? Now, that one, now you got to think about it. You got to go through these steps a little bit, right? So let's see. The probability of rolling a prime. So let's see. What are the prime numbers on a dice? So there's 2, 3, 5, and that's it. So it looks like, again, 3 out of 6, which becomes 1/2. Okay, so when you roll a dice, the probability that you roll a prime number is 1/2. All right, what's the probability that you roll? See how we're using that notation there, that P, and then in parentheses is the event that we're counting. So what's the probability that we roll the dice and we get a perfect square? All right, let's see. Did I roll a perfect square? So remember, a perfect square, if you take an integer and multiply it by itself, the result is a perfect square. 25 is a perfect square because it's 5 times 5. 49 is a perfect square because it's 7 times 7, right? So how can we roll a perfect square here? Well, let's see. 1 is a perfect square. It's 1 times 1. 4 is a perfect square because it's 2 times 2. And it looks like that's it. So we have 2 outcomes that match what we're looking for out of the possible 6. So the probability of rolling a perfect square is 1/3. Okay, so you see how that works? So basic probabilities, when we're dealing with simple situations, easier to count. Okay, pretty straightforward for how to do this kind of a problem here. Where are we? All right, now the problem occurs when, so remember, this requires equally likely outcomes. When you flip a coin, you're assuming the outcome is equally likely. When you roll a dice, you assume that the outcome is equally likely. When you pull a card out of a deck, you assume that it's equally likely. So for any of those, you would use the method that just occurred. Okay, but sometimes, like I mentioned, where are we? People try to apply this to methods that are not equally likely, and then it falls apart. So for instance, Steph Curry stepping up to the line. Playoff basketball, he's at the free throw line, and he's going to shoot some free throw, and we're sitting there watching the game, and someone says, what's the probability that he's going to make this? Well, this would be the wrong way to do it, right? If we try to apply what we just talked about to Steph Curry shooting free throws, we would be very, very wrong. right? So we would go, well, let's see. We're trying to count how many ways can he make the basket. 1, the ball goes in the basket, right? Okay, and how many outcomes are there? What is the size of the sample space? Well, the sample space has size 2 because he can either make the basket or he can miss it, right? If the ball does not go through the hoop, it's a miss, right? So if there's one outcome that he makes it and the sample size is 2, doesn't that mean that the probability of him making it is 1/2? Right? That's the wrong logic to use because the outcomes are not equally likely. We're applying the wrong tool in the wrong situation. The likelihood of Steph Curry making a free throw is very, very high, right? Why? Because the outcomes are not equally likely. He has spent many, 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 many hours of his life shooting free throws, and he's gotten very, very good at it. So we cannot apply the equally likely outcome to Steph Curry shooting free throws because it's not equally likely that he makes it or misses it. Okay, but that's the kind of logic that you see people use regularly when they're first learning probability because they get used to this calculation. So then how would we calculate the probability of Steph Curry making his free throw? Well, they probably walk you through it when they're talking about it, during the basketball game. What you would do is you would look at the past observations. So you would look over the course, and you could either look over the course of the playoffs or you could look over the course of the entire season, however you wanted to break it down, depending on what you were talking about. But you look at the actual events that have happened in the past. So how many times did Steph Curry make a free throw versus how many times did he try a free throw? Right? The procedure of him shooting a free throw is the experiment that's being repeated. Him making it, we're keeping track of that. So, if he's made, whatever, I don't know off the top of my head what his free throw percentage is, but let's just say it's around 90%. If he made around 900 baskets and he shot around 1,000, then we would simplify that down to around 90%, around 0.9, somewhere in that neighborhood would be his free throw percentage, right? So you kind of have to think about, is this like a theoretical classical outcome where I'm flipping a coin, I'm rolling a dice where all outcomes are equally likely, or am I in a situation where the outcomes are not equally likely and I have to take the past information and calculate the probability that way? Always have to ask yourself that, because if you try to use the wrong one, obviously it's going to be wrong, right? And they even say that right here. Caution, when using classical approach, always verify that the outcomes are in fact equally likely. Right. Let's see. Yeah, we don't need those. The law of large numbers. This is an important idea in probability that makes a lot of what we do in statistics work. So the law of large numbers says that as a procedure is repeated and again, the relative frequency probability of an event tends to approach the actual probability. Now that sounds kind of confusing at first, but what this means is, this is why, I wanted a larger sample size before I would release the results from the survey, because you have the extreme end of statistics, which is anecdotal evidence. You have a sample size of 1. No one is ever going to take your statistics seriously if you have a sample size of 1, right? That would be like I say, okay, everybody, I have this coin, and it's a fair coin, and it has heads and tails, and I'm going to experiment to see what the likelihood of getting tails is. So I flip it one time, the coin comes up tails, and I say, well, I ran the experiment one time, and it came up tails one time. That's 100% of the time. So 100% of the time you flip this coin, it's going to come up tails. Everyone would think that's ridiculous, right? The reason it's ridiculous is because I took the smallest possible sample size. What this is saying is, as we increase our sample size, as we increase the times that we repeat an experiment, the probability that we observe will be closer and closer to the actual probability, right? So when we're in class, I usually hand out pennies, and we do like coin flipping experiments, because actually flipping some coins can, for an hour under different, doing different exercises with it can really help make a lot of sense of probabilities. So for instance, let's imaginary right now, because I have to kind of summarize. Let's say you all have a penny in front of you, and I say, everyone flip your coin 10 times, and then count the number of times that you get tails. Well, we would expect there to be a range, right? But like, what would you expect to see the most of? You'd kind of expect to see a lot of 4s and 5s and 6s of tails, right? Because we kind of know the probability should be about half the time you should get tails. So if you flip a coin 10 times, you would expect to see a lot of 4, 5s, and 6s for tails. But what if you got a 3 or 7? Would you be shocked? Would you be like, I got to call the newspaper. I flipped a coin 10 times and I just got tails 7 times. Can you believe that? No, you wouldn't be that shocked, right? It's even possible that if we did this experiment, someone in the room might actually get tails all 10 times, right? You wouldn't be that shocked. You wouldn't like start calling your family members and go, this person just flipped a coin 10 times and got tails all 10 times. Can you even believe it, right? It wouldn't be that shocking. But what if we all were in a room and we flipped a coin 1,000 times and someone in the room got tails 1,000 times? That's pretty unlikely, right? That would be shocking. That would be like, okay, what is going on here? So you sort of intrinsically understand the law of large numbers. The more times you do something, the more times those probabilities are going to even out to where they should be. In a short-term experiment, you can make those probabilities misrepresentative, right? Even if I flip a coin 5 times, it comes up tails 5 times, and I'm like, look, that's it. 100% of the time, this coin comes up tails. You wouldn't really be convinced, right? But if I flipped it 1,000 times and it came up tails 1,000 times, then we'd start scratching our head and going, something is going on here that we don't quite understand, right? We would get weird about it. So that's that law of large numbers. The more times you repeat an experiment, the more times the probabilities are going to come out the way they're supposed to. Now, here's your caution, because there's this other thing that people come up with related to the law of large numbers. It's basically a misinterpretation of the law of large numbers, and people do it wrong, and it's used against people. I thought there was an explanation in here, but I'll talk about it. So the law of large numbers is totally legitimate, and like I've said, it's even somewhat intuitive. We kind of understand it, like the coin flipping I was just talking about. But caution, the law of large numbers applies to behavior over a large number of trials, and it does not apply to one outcome. Don't make the foolish mistake of losing large sums of money by incorrectly thinking that a string of losses increases the chances of a win on the next bet. So what they're referring to is what you often hear called the law of averages. And it's kind of interesting once you learn statistics, because you'll hear people talk about the law of averages and they'll go, oh, well, by the law of averages, this. But the funny thing about the law of averages is that it's wrong. Right? It's got a name, the law of averages, but it is scientifically incorrect. So you shouldn't be using it. The law of averages is basically, people think that the law of large numbers has to pay off in the short term, but it doesn't. The law of large numbers says it pays off in the long term. If we do lots and lots of experiments, the probabilities are going to get where they need to be. But it doesn't say that's going to happen immediately. This happens, when I was younger and you'd first go to casinos, they'd have the roulette table, and when I was, it was way back in the day, they didn't have any signage on the roulette tables. Now, if you go to a roulette table, there is always a big sign there that tells you what the past results are, right? It tells you either red, red or black, right? And you get the occasional green number on there. It tells you the numbers that are coming up, but even more, it tells you the color, because with roulette, you can bet on either a number or you can bet on a color coming up. All the numbers are colored either red or black, and then there's 2 of them that are green. Sometimes one's green, but most of the time now there's 2, because it favors the house a little bit more to do that. So they put up a big sign that tells you the past 20 results, right? And the reason they do this is because they figured out that people think they understand the law of averages, which again is not a valid law. It is incorrect. But they walk by and they see that sign and they're like, wait a minute. Black has come up 7 times in a row. Oh, red's due to hit. So then they bet on red. But it doesn't work that way. The law of large numbers does not work that way. And the law of averages I've mentioned is false. Think about it this way. That little ball they do on the roulette table and they throw it on there, it doesn't have a memory. right? It doesn't have a brain. When that ball is going around the ring, it doesn't say, I've come up on a black number 7 times in a row. It's probably time that I land on a red number. It's just a little piece of marble. It doesn't like think about it. There's no memory being like the universe doesn't keep track and say, okay, this time marble, you land on a red. It doesn't work that way, right? What it says is if you roll that roulette ball 10,000 times, then you're going to get close to half. It'll be just under half because of the greens, but you'll get really close to 1/2 for the probability for each of those. It doesn't say on the next roll it's going to catch up. And that's why they put it there, is because a lot of people incorrectly interpret the law of large numbers as the incorrect law of averages, and they go, oh man, eight reds in a row, I'm betting on black this time. And then that's just the casino makes more money that way, because that's what casinos do. They just get you betting. Every game in the casino has a slight edge for the house. So their whole goal is to just get you to bet more and more money, because eventually it ends up with them. And by putting the sign up for roulette, people incorrectly interpret the law of large numbers. They bet money and lose. So that's what he's saying. Don't make the foolish mistake of losing large sums of money by incorrectly thinking that a string of losses increases the chance of a win on the bet. Just remind yourself, that ball doesn't have a brain. It doesn't have a memory to know what the last 6 outcomes were, and that it has to it's not the ball's job to make it even out, right? It doesn't work that way. Let's see, a couple minutes. What can I say before we go? Yeah, we don't want to get into compliments yet, and we'll get into that next time. That's a whole can of worms that starts to get confusing when we start getting into those definitions. So we will continue that next time. Yeah, we'll continue this discussion next time with probability. Oh, I was gonna mention. Let's see. I better extend that. So notice that the project that you're going to do at the end, the part of your project you're going to do at the end of this chapter, it's open. It's statistical conclusions. It's not probability based. Most of the time I try to line the chapter up with what you're doing, but you're probably not going to be directly calculating probabilities for your project. You're going to have StatCrunch calculate the probabilities for you, and you're going to use those probabilities to make interpretations. So what you should be doing here is starting to put together your statistical conclusions. Now, they don't have to be perfect here, but you should start asking yourself, what should my statistical conclusions be, right? And this can come from a number of things. If you remember last time we were talking about the correlation and regression. If you did your correlation and regression part, where is it? Chapter 4. Yeah, if you did this stuff and you did, your correlation piece right here, talk about your conclusions. Like, what is the conclusion? A lot of people think, well, I've made the graph, so I'm done, right? No, the graph is a nice visual that supports your argument that you're trying to make, but without the argument, the visualization is nothing, right? How often does someone just come up to you and hand you a graph and then walk away? No, they hand you a graph because they're trying to make a case for something. They're trying to get you to vote a certain way. They are trying to change your mind about something. They are trying to make an argument, and they use the visual to support that. So just making a scatter plot with a line on it it's nice and it supports your evidence, but it's useless without some type of conclusion. So you want to start putting those conclusions together, right? For instance, yes, we believe that our scatter plot and our line of regression support the claim that in general, students who have larger shoe sizes are also taller, right? Or students who worked a lot of hours take less units at school, or students who work a lot of hours take more units at school. Like, whatever your conclusion is from your data, you want to start putting those together. Now, you can change these. I'm not going to come in and judge them in here and say, like, nope, your conclusion is wrong. The point of this is for you to start thinking about those conclusions, because you're really kind of going to be putting those together when you do the actual project. But you want to start thinking about them. Think about your scatter plots that you made and think about, like, what is this telling me? What is the conclusion that I can put on this scatter plot? Like, what is the narrative that I can put together that this scatter plot supports? That's what you want to be thinking about here. Okay, that's what goes here. And you can use other tools as well. All right, so that's what you want to be thinking about. You've got a little bit of time before that one's due, but you're going to be working through this probability section. Don't be afraid to get help. Some people get completely thrown sideways by probabilities. It is confusing, right? Probability problems, like I said, can get complicated quickly. So make sure that you're getting help from me or the Tutor Center if you have any questions. Okay, thanks everybody. I'm going to shut down the YouTube stream. I will, in fact, I think it's office hours today, right? It's Tuesday. So it is office hours. Also, you're always welcome to come talk to me after class. If you want to hop into Zoom and talk to me, come do it, and I will answer whatever questions I can for you. Okay, thanks everybody.